today's topic is also solid oxide fuel cell, which we have been discussing for the last couple of lectures. In addition, we will also talk about something related topic, it is hydrogen generation through MIEC reactor. We will discuss what is the MIEC reactor later on, but to start with we will let us talk about the solid oxide fuel cell once again. The thing which we have discussed earlier is the following. This was the anode supported single cell. It is basically a plate like structure, a sandwich structure. The basic support structure is anode. We have a very thin layer of electrolyte which you cannot see on this surface, it is actually almost like a transparent material, and then on the top the black layer what you see is actually a cathode layer, the bottom layer is actually the anode layer. So, this has been prepared in CJCRI, it was prepared in CJCRI and I had some of the pictures of that. So, this I have shown you earlier. This is the typical microstructure of the cross section, as you have discussed earlier, that the anode as well as the cathode is a porous structure, and in between you have a dense electrolyte, YSZ electrolyte. In this particular case it is about 20 micron thick. In addition, we have a fourth layer here which is called the cathode functional layer. This in this case it is about 10 micron thick, and it is a basically gadolinium doped ceria CGO interlayer. So, this is the typical structure, and of course, it is single cell. And then we also discussed about their electrical characteristics. Two typical structure, two typical current voltage plots have been shown here. One is the YSZ or the electrolyte thickness is about 35 micron, the other one is still less, about 24 micron, and this is a typical curve. This is the open circuit voltage, it is slightly more than 1 volt, about 1.1 volt, very close to 1.2, but that is when the current is 0, that is with no current is being drawn. But as soon as the current is being drawn, the current increases, current is on this side, current increases and the voltage drops. That is the typical characteristics or the normal characteristics of any fuel cell. As soon as the current is being drawn from the cell, the open circuit voltage, this is not the open circuit voltage, but the voltage drops, and somewhere here you actually get the maximum, not the maximum, this is a standard practice that at about 7.7 volt whatever the current is drawn, that is the operating current. So, with this consideration one gets about 1.2 amps per centimeter square at 0.7 watt per centimeter square. If you just multiply the ampere to the voltage, you will get that. If you reduce the thickness of the electrolyte, which is a very important criteria of any fuel cell, if you decrease the thickness, there is a possibility of drawing higher current 1.55 amperes at that same voltage, and you get about 0.9 watt per centimeter square. That is the current density or power density one can expect from this kind of single cells. Of course, this is not, it depends on the type of fabrication technique, it depends on the interface characteristics, it depends on many different parameters, porosity, pore size distribution, the interface characteristics, and so on and so forth. So, there are many different parameters to be controlled or optimized to get the best possible results. With this background, let us go to the advantages and disadvantages of the two designs we have discussed so far. The tubular design advantages are like this. This is the typical stack, a large number of tubes, one enclosed tubes. The tubes can be as long as 2 meters long and about 2 centimeter in diameter. So, no gas sealing is required because the two chambers are already separated by the tube wall. So, there is no special effort needed for separating the two chambers. The easy connection between cells possible. With this kind of a technology, already pilot plants or the demonstration plants have been fabricated and demonstrated that up to 3 kilowatt, in fact, there are much larger plants have been erected up to 250 kilowatts, but a 3 kilowatt stack would consist of 24 cells of 1.5 meter length. So, this is a typical dimension and the volume of the material used. There are quite a few disadvantages, of course. Disadvantages are like this: relatively long current path, because the connection is only on the one end. So, any current generated or a oxygen is being transported here, at the end it has to the electron has to come all the way to this. So, the current path is too long, little higher resistance path, and therefore, the cell leading to high internal resistance and thereby resistive loss. So, even though the film thickness, the electrolyte thickness itself is very small, maybe up to 20 micron, but the current has to pass or travel through a longer distance because the length of the tube, and therefore, this is relatively lossy, or the internal resistance, overall internal resistance becomes relatively high. The support tube adds weight and volume to the cell, leading to reduced power density. Okay. One of the driving force for fabricating or developing a technology of fuel cell is basically high power per unit mass. However, here the tube, the cathode, particularly the support tube, is relatively thick, and when you are making 1.5 meter long tubes, the strength of the tube has to be sufficient, and therefore, you need sufficient amount of material there. So, that increases the weight, the dead weight of the material, because as such the cathode is not taking part in the, except the interface, the rest of the material is not taking part in the electrochemical reaction. So, it is about 0.2 to 0.3 watt per centimeter square. That is more or less the power density one gets. Manufacturing cost is high because it needs a CVD, thin film deposition technique, and a quite elaborate fabrication technology is required for fabrication of these tubular structures. So, the application is restricted to stationary power plants primarily, because that has been designed for this particular technology has been designed only for the stationary power units, auxiliary power units, or the captive power units like that. So, that is one of the maybe one of the limitations, but one can build much larger capacity of power plants. Next we come to the planar design. What are the advantages and disadvantages of that compared to tubular design? Because tubular design has been practiced by certain companies, certain research labs, whereas the planar design is being pursued by a separate group of researchers. So, high power density, one can get a much larger power density up to about 2 watt per centimeter square. Of course, the manufacturing cost is relatively low. This has been given in US dollar, about 800 kilowatts, but it is still not sufficient for commercialization. The target is about less than 400 US dollar per kilowatt. That will be the ideal situation under which this kind of technology can be economic under the current economic condition. The compact design and light in weight, as we have mentioned, compared to the tubular design, it is relatively compact and relatively light in overall weight. Less energy loss because the current paths are limited, current paths are relatively short, so less energy loss. Simple to fabricate, well, because it is not a tubular construction, it is basically a plate like construction. So, generally it is assumed that it is relatively simple to fabricate the ceramic structure. Flexibility in cell geometry like circular, square, rectangular and hexagonal shapes. So, one can make different kind of geometry so far as the surface area is concerned. So, one in order to make it a much more compact structure, one can make either a rectangular cross section or even hexagonal shapes. So, that may be tightly fitted into one another. Better quality control possible with respect to component fabrication, because they are relatively smaller in size and therefore, uniformity of the properties may be little better. Diverse application feasibility like transportation, military and stationary. In addition to stationary, we have seen in tubular the primary application area is stationary power plant, whereas in case of planar one can think of other possibilities also, particularly the transportation. In fact, some companies have already fabricated what they call APU, auxiliary power unit, for the automobile sector. So, in addition to the motive power, basic power is once again the IC engine, but in addition today's automobile industry or a particular car needs lot of electrical power for running many electronic gadgets, and therefore, that electronic power can come from the fuel cells. So, that is what we call the auxiliary power unit, and that auxiliary power unit has been demonstrated with solid oxide fuel cells. This has not been possible with tubular designs. Of course, there are once again few disadvantages. The main disadvantage is the non-availability or the requirement of a glass sealant, because separation of the two chambers becomes quite difficult. In a tubular configuration, it is quite easy, whereas in a planar configuration is not that easy. So, you need to separate these two chambers of the fuel chamber and the oxidant chamber or the air chamber through some sealant, high temperature sealant, and the only option we have is a high temperature glass. Unfortunately, some amount of several glass compositions are available for this kind of purpose, but none of them are quite fully satisfactory. Either there is breakage because of the cycling, thermal cycling, or there is some reactions between the components. So, that problem still exists, but a lot of development has really taken place, and one can use some of the glasses available. So, many of these glass compositions have been patented by different glass companies, including Schott from Germany. Well, that is the structure of the planar configuration which we have shown earlier. So, it is basically these are the two advantages, one is the glass seal and the cell degradation. Cell degradation is also a problem, that means the overall life is little limited. So, these are the two disadvantages so far as the planar design is concerned. Next, we have so far discussed about the single cells, how it performs, how it depends on the different geometry, how it depends on different materials, and what are the different structures available to us both in the tubular form as well as the planar form. Now, as I mentioned earlier, the overall the open circuit voltage of each single cell is nearly little more than 1 volt, and it normally operates at about 0.7 to 0.8 volts. So, that is not useful so far as the power plant is concerned or a power unit is concerned. So, we need stacks of several such single cells, and these are the kind of stackings one normally uses. This is for the tubular cell. These are the cross sections of the tubular cell. These are 6 tubular cells have been put together here, and as I mentioned earlier in the last class possibly, this is the interconnect material. So, the protruded interconnect actually it connects the cathode on this side and the anode on this side. So, the internal surface is connected to the external surface of the next tube. So, this is vertically it is a series circuit, whereas horizontally it is basically a parallel circuit, because the anode is connected to the anode and here also the anode is connected to the anode. So, a battery, the overall power system will consist of a large number of series and parallel connections of individual tubes, and that is how actually a stack is produced. In fact, fuel stacking here, once the single cells or single tubes are fabricated, stacking is relatively easy in this case, and in between you have the connections, high temperature contacts basically, but generally it is actually nickel felt, some kind of a nickel felt, which also acts as the vibration absorbers. So, it is used as a cushion, and on this side you have a cathode bus and the anode bus. So, this bus is connected to the anode, all the anodes, and this is connected to the cathode of individual tubes. So, that is how a stack is normally generated. In fact, next picture gives you another view of that. This is actually the magnified view of this particular region, but in general it will look like this, a large number of tubes just stacked over one another. That is the normal way one can put a stack. So, stacking is relatively simple, and of course, you have gas connections which is not shown here. There will be manifolds for gas inlets as well as outlets from one of the ends, okay, because these are normally closed end tubes. So, gas has to come from the other side and then go outside. So, those manifolds have to be put in place. Well, going back to the planar design of course, the stack fabrication is little complicated. Sorry. This is the single cell, and this is what we call the interconnect. So, it is basically a stacking of these several plates, unlike its tubes, these are all plates. So, this particular single cell is fixed on a in this case on a steel plate, grooved properly. So, it is exposed on both sides. This is the cathode side and the bottom side is actually the anode side. So, exactly the dimensions have to match, okay. These dimensions have to be matched, and this there should not be any leakage of the fuel or the air, and therefore, this has to be sealed with some glass cells, okay. So, that is one thing. The other thing is, this is your interconnect, that means I have shown you earlier that there are grooves on both the sides. This is one kind of groove, and below also there will be another groove. So, that groove may be a crosswise or in the parallel grooves, but on one side the fuel passes through the grooves, on the other side it is the air which passes through the grooves. So, this is of course the expanded view of the vertical directions. Ultimately, it actually has to be sit over one over the other. So, it will be a compact compact configuration, and there are some vertical holes. You can see these vertical holes coincides with each other, and finally, they form a manifold. Okay. So, through one of those holes the fuel enters and comes on this surface, the top surface, because the bottom here is the anode and the top of the black surface is actually the cathode. So, this top surface on this plate is actually the channels for the fuel, and the bottom surface on this plate is actually for the air. So, that is what is happening here. The blue lines actually comes and goes on the top side of this single cell, and it is the end plate. This is a end plate which actually encloses the air channels. So, all these plates are stacked over the another, and in between there are very small channels. These channel designs are of course also very important. The channels can be designed in many different ways. We are not discussing here, but one can design it in different ways, particularly the depth of the channel, the width of the channel, and whether it should be uniform or it can be little taper, and so on and so forth, because as the fuel enters or fuel or the gas enters on one side, it immediately reacts on that side, and less and less amount of the gases are available as it flows across the channels. So, the channel dimensions are very important, the flow rates have to be uniform, and the consumption of the gases are also have to be uniform over the whole area of the electrolyte or the plate or the single cells. So, those utilization of the gaseous fuels are also very have to be fully utilized, and therefore, the channel dimensions or channel designs are of very important, and therefore, one has to have a lot of possibilities in such cases. Okay. So, this is the stack, and these are only two single cells have been shown here, but one can have a large number of stacks, large number of single cells, up to 100 cells one can imagine. So that they are all, and such cells again can be, these are all series connections, and that kind of stacks can be put together in parallel connections as well. So, this is slightly complicated. The stack design in case of planar concept or planar configuration is slightly complicated than the tubular concepts, tubular designs or the tubular configuration. So, stack design in case of tubular configuration is quite simple, whereas stack design in case of planar is little more complicated and fabrication is little difficult. That we have shown earlier. Now, when we are talking about stacks, you need, in addition to the anode, cathode, electrolyte, and we have also discussed some materials used as cathode functional layer or anode functional layer. In addition to all these materials, two more important materials are also have to be used for stack design or stack fabrication. As I have just shown you earlier, the earlier slide, nickel felt is just a simple thing which one can use between the tubes, which in case of a tubular design. In case of stacking of tubes, only need additional material, what is needed is a nickel felt. Okay. So, that can be, that is the only thing one needs. In addition, of course, the other chambers or the manifolds and so on, some metallic manifolds are also needed for supply of the gases or taking out the exhaust gases and so on. But otherwise it is simple nickel felt for the tubular design. Whereas, in a planar design you need two important materials or two groups of important materials. One is the interconnect, which I have shown you earlier. This is the interconnect material, these plates are actually interconnect materials, and this material is one additional material in addition to cathode, anode and electrolyte, and the other material is, which also have been mentioned, is the is the sealant, okay, high temperature seal. So, these are the two groups of material, and there are various different materials have been tried out. I will give you more details of this in another slide, and but this one, so far as the high temperature seal is concerned, as has been mentioned, that they are basically high temperature glass or glass ceramics. Most of them after cooling actually gets crystallized to some extent and forms glass ceramic seals. And one of the major problems here is the thermal expansion matching of the thermal expansion between the metallic interconnect, if it is a metal is used as the interconnect material, and the ceramic electrolyte plate or the anode plate, okay, anode or cathode plate. So, one aspect is to match the thermal expansion coefficient between the three active materials like electrolyte, cathode and the anode, and then the inactive or passive materials like the interconnect has also to be matched. The expansion coefficient of that has also to be matched with the overall membrane electrode assembly MEA, and there the sealing material also have to be properly thermal expansion coefficient also have to be properly matched for the sealing material, the MEA as well as the interconnect material. So, all of them have to be properly adjusted, and therefore, the composition is of great importance here. Composition also has an importance so far as the softening point is concerned or the glass transition temperature is concerned. So, since the operating temperature is about 700 to 800 degrees centigrade, the softening point has to be relatively high, okay, otherwise there will be leakages. So, these are the normal oxides used for making these glass compositions. These are typical glass composition, but there are many different glass compositions have been tried out. One important aspect is there is no alkali here. Alkali is normally for normal glasses, alkali is one of the basic components which reduces the melting point or the softening point of glasses, but in this case there no alkali is allowed, whereas and that makes the melting as well as processing of these glasses are quite difficult. So, the typical composition here is about 35% mole percent, barium oxide 15 mole percent, calcium oxide, aluminum oxide 5 mole percent and some borate and silicate. Okay. So, 10 mole percent of B2O3 and 35 mole percent of SiO2. So, this is a typical composition, but there are a lot of variations, a lot of different things can be added to this. Sometimes titania or zirconia can also be added, so that they become crystallized, and by crystallizing actually you change them. So, the crystallization property is important to be controlled, so that one can control the thermal expansion coefficient. We will discuss about the interconnect later on in slightly details. Oh, it is there. So, these are the different kind of interconnects people have tried over the years. One started with perovskite oxides, because since most of the other materials are basically oxides or ceramic material. So, a natural choice was to find out a high temperature oxide which is electronically conducting, and one could find out this kind of a compound, again a perovskite compound, lanthanum chromite. So, lanthanum chromite has a fairly high melting point, and at high temperature it has a very good electronic conductivity. So, what is needed here of course is to separate the two chambers, the fuel chamber and the air chamber. These have to be separated out physically, that is one requirement, and the other requirement is it has to electronically connect the cathode side to the anode side of the next cell. So, electronic conductivity also is very important at that temperature. If the electrical conductivity is low, that means you will lose a lot of power. So, electrical power will be lost if the electrical conductivity is not good enough. So, therefore, lanthanum chromite has been found out as one of the good electronically conducting material, and also it has a higher melting point. So, it withstands, it does not really make any undergo any changes at the operating temperature of 800 to 900 degrees centigrade. It is not only pure lanthanum chromite, but some dopants can also be used for the purpose of sintering aid, or because it has to be again like the electrolyte. This material also have to be a very dense material because no gases, there should not be any molecular diffusion through this material between the two chambers, two enclosures. So, one needs a very high density material, and to proper densification some of these dopants can also be used, and the general formula is lanthanum 0.9, it is slightly deficient in lanthanum oxide, that makes the sintering better, and chromium can be replaced by metals like aluminum, magnesium and calcium. It is only about 0.1 mole percent. Okay. So, this is how the material is prepared. However, this is not a current level of thinking, or currently lanthanum chromite is not being used more because one of the reason why the lanthanum chromite is not being used in the later versions or in the current fabrications, that is the chromium diffusion. When chromium comes in contact with zirconia or the cathode material or the anode material, the chromium diffuses in, and that creates aging problem. So, deteriorates the cell characteristics. So, that is one of the reason why lanthanum chromite is not a very preferred material at this point of time. Instead, people go for metallic interconnects. Large number of different high temperature metals and alloys have been tried out. For example, chromium based alloy, chromium 5% iron and 1% yttrium oxide. This is so it is actually a oxide dispersed alloy. It is called alloy and creates chromium scale in long term and operation at 900. So, this also creates impact. Chromium oxidation takes place on the surface, and sometimes it is better, it actually stops further oxidation of the same metal, but once again the chromium creates problem so far as the cell components are concerned. So, this is then another material also have been used, which is oxidized again at about 800 degrees centigrade, and this is iron 26% chromium molybdenum alloy. So, many different alloys have been tried so far as the metal interconnect is concerned, but in between the temperature of operation of the cells have also come down. So, earlier it was the normal operating temperature was 900 degrees centigrade, now it is less than 800 degrees centigrade. So, that makes it possible to use other alloys like the best material so far is actually ferritic steel. So, instead many different alloys have been tried, but ultimately people have settled down for the ferritic steel, which is basically 20 to 24% chromium alloy. Okay. So, these are also chromium containing alloys. So, most of them have chromium containing alloys, but this has a better property and better oxidation resistance property than the other steels or alloys, and of course, the thermal expansion coefficient matching is another very important aspect. So, in general the alloys or the metals have a higher thermal expansion coefficient and compared to the oxides, and that is one of the problems of course, but the current trend is to use ferritic steel instead of the other exotic alloys mentioned above. Well, let me change the topic to some extent. We have not discussed the details of how the materials are prepared in the powder form and so on, particularly although I mentioned very briefly that these are anyway ceramic powders, whether it is zirconia or YSZ or LSM like lanthanum manganite or nickel YSZ. Okay. So, these are basically the starting materials are always powders, and they can be synthesized by many different techniques like solid state sintering is one of the oldest techniques one can use, ceramic processing technique one can use because they are basically mixed oxides. So, two of the oxides of concern can be put together or mixed together and put at the high temperature. So, there will be a high temperature chemical reaction and the mixed oxide will be formed or a solid solution will form just like YSZ. There are other of course much better techniques where much finer powders can be prepared by either by co-precipitation or by sol gel technique or maybe combustion technique. Okay. So, it is a high temperature combustion or either a solution combustion or gel combustion. So, many of these techniques can be used to make fine powders of these mixed oxides, and they can be when you talk about the anode is basically a nickel YSZ. So, nickel and YSZ normally YSZ powder and nickel oxide are put together and mixed together and then heated at high temperature to make a composite nickel oxide YSZ powder, and then during its use because it basically faces the hydrogen or the reducing condition. So, during its use the nickel oxide gets reduced to nickel and finally, the structure remains as nickel YSZ powder. So, I am not going to the details of these powder preparation techniques. I am trying to concentrate on a particular technique of preparing nickel YSZ composite, nickel YSZ Sarmet composite, which is used as an anode material. Now, I mentioned earlier that one of the reasons why nickel is used along with YSZ is it is facing a very reducing conditions, very extreme reducing conditions like hydrogen, and whatever anode material we choose it has to be chemically stable or thermodynamically stable at this temperature and the reducing condition. So, nickel actually provides the electronic conductivity because YSZ at this temperature does not have any electronic conductivity, and it produces a fairly large resistance until unless it is fabricated in a very thin form, thin film form. So, that is the reason electrolyte on the same material it can be used as electrolyte, but it has to be used as a very thin section, whereas anode is not that thin section, and particularly the anode supported system, anode supported structure uses about 1.5 millimeter, 1 millimeter to 1.5 millimeter thickness of the anode. So, that itself has a very high resistance when you have YSZ as one of the components. However, one YSZ is used primarily to maintain or to match the thermal expansion coefficient with the electrolyte. So, only nickel oxide or nickel cannot be used, although it gives a good electrical conductivity, but it cannot be used 100% nickel oxide or 100% nickel cannot be used. So, nickel and YSZ both of them are required for two different purposes. The purpose is as much, or the idea is, or the target should be as little of nickel is used, so that the thermal expansion matching becomes easier or better, okay. Because rest of the thing is YSZ. So, YSZ has a good thermal matching with the electrolyte, because the same material is also used as electrolyte. So, our idea should be to use minimum amount of nickel and get the good connectivity, so far as there is a good thermal good electrical continuity. So, that is an idea, that is the kind of target, that we should not use too much of nickel in the system, so that the thermal expansion coefficient goes away from YSZ. So, we should use very little of nickel and even then good electrical conductivity. So, there must be a continuity, that means the particles of nickel should be in touch with each other. So, that is for that, so that there is a percolation of charges, and that is one of the targets. And normally one uses nickel and YSZ just mixed together, which may or may not give the right kind of connectivity. Here a particular technique has been used, which we call the synthesis of anode powder by electroless technique. Let me try to describe this process. This is a very simple process where the YSZ powder has been coated, each of the individual YSZ powders have been coated with nickel or metallic nickel, right. So, that you get every YSZ is coated with nickel, and whenever such nickel coated YSZ powder are pressed together or put together or tape cast, whatever the technique of fabrication is used, the nickel and nickel contacts will be ensured. This is show that with this idea, this kind of electroless nickel coating has been used. Electroless nickel coating, there is a technique by which a metal can be deposited on a non-metal without any electrical EMF. So, that is the reason it is called electroless technique, and it is very simple technique. You take YSZ powders, it is put in a solution, or it is called sensitization and activation. So, these two purposes are served by stannic chloride, stannous chloride SnCl2 and palladium chloride. So, these actually act the activation, and this acts as a kinds of sensitization. So, one after the other you just add. So, SnCl2 plus PdCl2, this is the kind of reaction one expects. So, it forms stannic chloride and palladium metal. Palladium metal is deposited on the surface of the YSZ powders. Okay. So, then of course, it is washed with the deionized water, and then finally, these sensitized powders, that means kind of palladium coated powders, are put in a nickel bath, nickel solution bath, okay, nickel nitrate solution, actually nickel nitrate, ammonium nitrate and some reducing agent like hydrogen hydrate. So, in such a bath, of course, it has its a particular composition have to be used, and such sensitized powders, YSZ powders, if you put in this kind of a solution, the nickel coated YSZ powders will be available. So, one can, instead of random mixing of nickel oxide or nickel, normally as I mentioned earlier, it is the nickel oxide and YSZ is mixed together and then heated to high temperature to sinter it, to make a bonding between them, and then nickel oxide is reduced in a hydrogen atmosphere, so that nickel is produced. It of course helps develop the porosity as well. Once nickel oxide is reduced to nickel, then oxygen goes out and it produces sufficient amount of porosity. That is also an advantage. Here we are not randomly mixing the two phases together, but in a structured manner. In a structured manner, we are putting the nickel coating on the individual powders. So, that is possible by this powder electroless technique. Yes, this is a kind of pictorial representation of what actually happens. This is bare powders, YSZ powders, then you put the palladium sensitization. Okay. So, palladium particles actually gets adhered to the surface of the YSZ, and then after the electroless solution it is put in the electroless solution, the nickel, a good coating of the nickel oxide, a nickel, metallic nickel. Now, this is not nickel oxide, this is metallic nickel is produced over YSZ. So, this how actually one get a nickel coated powders, and once you sinter that, you get a distinct boundaries. All the nickel, metallic nickels are at the boundaries, okay, surrounding the YSZ powders. The black is the YSZ powder, and the white regions are actually nickel, and you can see a very nice network forms as soon as you get a nickel coated YSZ powder. So, these are different volumes, volume percentages of nickel has been used, and as it increases the volume percent, thicker and thicker layers are formed. So, in 15 volume percent you can see much vivid grain boundary phases, and they are all forming a continuous network. And YSZ is usual electrolyte material, that is 8% Y2O3 and ZrO2. Now, the advantage of this kind of a structure is important, and one can see from this particular graph, where we have plotted and compared the conductivity, electrical conductivity of differently prepared nickel YSZ mixtures. There are 3 different types of mixtures have been prepared by different techniques. One is the normal solid state mixing, that is mixed oxide technique, that means nickel oxide and YSZ has been mixed together, sintered and then reduced in hydrogen atmosphere. Then we have a liquid dispersion techniques. Instead of a solid state dispersion, one uses a liquid dispersion where the dispersion becomes better. So, the distribution also becomes better, and the third one is in between, the coating technique, that is the electroless coating technique. So, what we have plotted here is the nickel volume nickel percentages against the conductivity. Okay. So, you can see this was a much lower conductivity for the same volume. Let us say if you are talking about 20 to 30%, 30 volume percent of the nickel, you can see the conductivity is much lower for the mixed ion, the prepared by the solid state mixing. The samples which have been prepared by solid state mixing has a much lower conductivity, whereas the liquid dispersion technique has a slightly higher conductivity, and the coating technique which I have discussed just now has a much lower, much higher conductivity, and that is a very interesting observation, because you have a continuous network, and in other cases you really do not get a continuous network. There are nickel dispersions, but the continuous network is not available there. So, and you can see here it is quite effective so far as this volume percentage is concerned, right. So, we get this kind of conductivity is available at a much lower concentration of nickel oxide or nickel, metal dispersion nickel, and that helps to match the thermal expansion coefficient with the electrolyte much better. So, this is a technique which has been developed at CGCRI while I was there. Okay. So, this is the advantage of electroless nickel deposition on OISZ powders. I will finish this discussion on SOFC by another couple of slides. Is nanotechnology and SOFC with the introduction or the development of the nano concept. It has a bearing on the SOFC also, SOFC performance and SOFC development also. Here is I will just give you some statements, some information only to share that a nanotechnology can be introduced and can be utilized or the concept of nanotechnology can be very well utilized for the development of SOFC or the improvement of the performance of the SOFC. Extraordinarily improved oxygen ion conductivity, this is log sigma of the order of minus 1.2 at 600 degrees has been observed with lanthanum gallet film. This is not OISZ, of course, this is not OISZ. I mentioned earlier that just like OISZ or ETS stabilized zirconia, there is another compound called lanthanum gallet which has a very high, in general very high conductivity at a much lower temperature. But if the same material is deposited in the nanometer size of the thickness of 370 nanometers, you get a much enhanced conductivity at 600 degrees centigrade, which is much greater than that of OISZ. So, and if since the thickness is smaller, about 370 nanometers, one can get a much enhanced conductivity. So, that is one advantage gets if you take just the concept of nanometers. Using 400 nanometer SDC, this is cerium interlayers, okay, interlayer between LSGM. This is strontium and magnesium doped lanthanum gallet. This is pure lanthanum gallet. Here it is actually strontium and lanthanum that improves the expansion coefficient also, sorry, the electrical conductivity as such. Then thin one about 5 nanometer, I think it should be nanometer, and nickel ferrite SDC as the anode. Okay. This is the electrolyte and this is the anode supported. The power density of the order of 3 watt per centimeter square has been produced at 700 degree centigrade. Okay. So, this is an interlayer, of course, it is not used as a electrolyte, but it is an interlayer, and by using the concept of nanometer size particles or nanometer size films, one can get a power density of 3 watt per centimeter square. Earlier we have seen that the maximum power density is about around 1 watt or 1.2 watts per centimeter square, whereas in this kind of a configuration in or finer materials, one can get almost double the watt power density at a temperature of a much lower temperature of 700 degree centigrade. So, this is one advantage. Sorry. Similarly, this is for YSZ films, 30 to 300 nanometer thick films. Normally in our structures we have seen about 20 micron, but in this case we are talking about much thinner, about 30 to 300 nanometer thick YSZ films were prepared by oxidizing Of course, this kind of film cannot be prepared just powder metallurgy powder preparation techniques. One has to do something different, and that is why yttria zirconium alloy has been oxidized to form a very thin layer deposited onto a anodic nanoporous alumina substrates having a pore diameter or about 20 to 200 nanometers. So, once again the pore sizes are also quite fine, and using a DC magnetron sputtering. Okay. So, this is a little exotic processes. Commercially it may not be it may not be economic to do that, but just to demonstrate what kind of effect, what kind of advantages we get by thin film sputtering and so on. So, one can make impact micro thin film SOFCs like this. So, this has made it possible to use YSZ based SOFC to operate at a temperature of as low as 400 degrees centigrade. So, below 600 is very difficult, but one can get some this kind of an exotic materials or exotic fabrication technology, so that the temperature of operation can be as low as 400 degrees centigrade. Extraordinarily improved oxygen ion conduct, sorry, these are already been, I am sorry, it is going down. Why? Yeah. Another 2 points, it has been observed that power density improves substantially when the LSM and YSZ composite electrode morphology goes down to about 100 nanometer level. Okay. So, by reducing the morphology to 100 nanometer level, the power density can also be improved. And finally, the use of nano size powders is advantageous as electrode electrolyte co-firing is possible at lower temperature, at least 100 to 200 degrees lower than the usual solid state route of preparation. As if you remember that there is a co-firing technique for the anode supported fuel cells. Both the anode as well as the electrolyte are co-fired at the same temperature, where we expect that the anode should be porous and the electrolyte should be a completely dense material. So, co-firing has a very important role in fabrication of SOFCs. So, if you can reduce the co-firing temperature to about by 200 to 100 to 200 degrees, that certainly improves the total process and facilitates our fabrication technology. So, by use of nano powders or use of nano dispersions, one can really make a much better or improved technology, not only in terms of the characteristics, their electrical characteristics, but also the fabrication technology becomes little simple. So, by introducing the concept of nanotechnology, one can have a much better technology or a better performing materials so far the SOFC is concerned. So, with this we come to the end of our discussion on SOFC. We have discussed various technologies, various configurations, various materials and the fabrication technology and also their performance. Okay. Thank you very much for your attention.